All right, so as promised from the last video, I wanted to start with an additional trig equation problem, one that maybe involved a little bit more algebra. Okay, so we're going to start there. So find all values in the interval from 0 to 2 pi. Looking at the notation, include 0, don't include 2 pi, such that they will satisfy this equation. Okay, and the equation is sine theta times tangent theta equals sine theta. Okay, so looking at what's going on here, I somehow have to get theta by itself, but look at how many thetas are popping up in this problem. Theta, 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 okay? So similar to what we did when we had more complex algebra-based equations, ones without a lot of trig, we move everything to one side. So sine theta times tangent theta stays, and I'm going to subtract the entire quantity sine theta over to the left, setting it equal to 0, right? 0 has always been this powerful object for us. When we have it in an equation, it helps us when we go on to factor. And this does factor, right? If I think about this as two terms, I have everything to the left of the negative, or the minus sign, everything to the right of the minus sign. They both have a sine theta. So I can factor that out and write down what remains. Factoring out a sine theta from a sine theta, just like factoring out an x from an x, leaves you with a 1, not a 0. Factoring is like division, so sine divided by sine is 1. Once I have this factored and my operation between the factors is multiplication instead of subtraction, okay, now I can set each factor equal to 0 and have simpler equations to solve. There's one equation. The other equation, tan theta minus 1. Okay, so I'm going to take the easier one first. This is asking what angles in this interval. So once around the unit circle, there's 0, there's pi, halfway between is pi over 2. So each sort of quadrant here is half a pi. There's 1/2 pi, there's 2/2 pi's, here's 3/2 pi's, which we write as 3 pi over 2. And if I kept going, I'd be at 4 pi over 2, which is back to 2 pi. All the way around the circle is 2 pi. So I'm asking for when is the sine of theta 0? So what angles have a y value of 0 on the unit circle? So I'm just going to put that parenthetically. What angles, what thetas, have a y value, because that's what sine is, it's the y value, that was from previous video, of 0. Okay, so y value is the up-down amount, the amount we go vertically. So if I don't want to go vertically anyway, if I want my vertical value to be 0, I could be at this point right here, which is the 0 radians. Or I could be over here at pi radians, okay? So if this is not clear, this coordinate here is the coordinate 1, 0. Notice the y value is 0. The coordinate here is negative 1, 0. Notice again the y value is 0. So I get two possible answers from setting the first equation equal to 0. 0 and pi. All right, let's move on to the more complicated equation. Tangent of theta equals 1 when I move the 1 over to the other side, right? I'm trying to kind of figure out what is theta, so let's move some things around. Tangent, I think right now, if you already know how to solve this, that's great. You understand the relationship between tangent and the other trig functions. If I'm not there yet, and I think I can show a little bit more work and that would be beneficial, I'm thinking of tangent as sine over cosine. That is a rule that we've had since we first talked about SOHCAHTOA. Once I'm in this situation, let's undo the fraction. Multiply both sides by cosine theta. So I'm looking for, let me pause here, I'm not going to be able to isolate theta. It's not going to be able to be by itself. It wasn't by itself over here. But in this form, let's think about what this is saying. I'm looking for an angle whose sine and cosine are the same. Whose sine and cosine are the same. So another way of phrasing this is what angles, what thetas have, well, y value is the sine, have equal y and x values, because cosine is the x value. So thinking about unit circle, look at these. X and y are not the same value here. If I went up here, this is the coordinate 0, 1, x and y still aren't the same. So where are x and y the same? Okay, well that's going to be at this angle right here. My x value and my y value are the same. I'm getting an isosceles triangle. This should sound familiar, right? We've got two important triangles that we have to know. There's one of them. It's the 45, 45, 90 triangle. This is the only one that has two sides that are the same. It's the only one that's isosceles. Their sides are root 2 over 2. Again, things are only coming from our two special triangles. So I've got this root 2 over 2, this root 2 over 2. I know it's kind of sideways, but I'm trying to keep the same orientation here. Okay? What angle is that? Well, 45, 45, 90, but if the problem's in radians, my answer needs to be in radians. Radians is pi over 4. If you're still struggling to look that up, please make sure you devote the time to knowing this before the exam. So one possible answer, let me just keep building this list here, is pi over 4. But there's more, right? I can go anywhere on this unit circle. So, for instance, I can keep using this triangle right here. This triangle is not going to have equal sine and cosine, despite it being isosceles. And the reason is, here the x value is negative, but the y value is positive. So this is not what I want. But if I kept going, here's another one right here. Right, hypotenuse is always the radius, and I always have a height connecting me to the x-axis. Okay, that's how I know I can draw this correctly. On this triangle, the x value is negative root 2 over 2, so is the y value. So the whole question boils down to what angle is that? Okay, the reference angle is 45, but that's not the actual angle in standard position. So with all the markings I already have up here, it's not that difficult to figure out without doing a lot of computation or without doing a lot of memorization. This was pi over 4. It was a quarter of the top half of the circle. This is 2 pi over 4. This is 3 pi over 4. 4 pi over 4, one more, and I am at 5 pi over 4. So I'm just using the fact that I knew that this was a quarter of pi, and if I kept going this amount, I'll have 2 quarters, 3 quarters, 4 quarters, 5 quarters, and that's the last answer. So I get 4 possible values that satisfy this equation. Okay, I'm going to try to leave a unit circle up here. It might be useful as we talk about inverse trig, but it's a little big, so it may have to go at some point. But I'd like to have this visual when I'm referencing some trigonometry, just so we have something to point to, you have something to look at, and you don't feel like you're ever forced to memorize anything, right? We're just thinking about the circle as a tool, and if we're memorizing anything, it's the two triangles, 30, 60, 90, 45, 45, 90. So for inverse trig, we're going to start with a lot of background information that we've already covered. We're going to try to connect it to things that hopefully you already remember, or if you don't remember, you have to review anyway for the final, okay? So recall that a function is 1-to-1 if each output is paired with exactly one input. Okay, and when we talked about one-to-one functions, we talked about why they were important. Why did we care about this property? The property said that one-to-one functions have inverse relations. Relations are just rules, mappings, pairings that are also functions. So if I'm not a one-to-one function, my inverse is not going to be a function at all, and we'll start to have problems, okay? So let's look at trig functions. We looked at plenty of other types of functions that were one-to-one. E to the x is 1-to-1. Y equals x squared is not, because I can have two inputs paired with an output. Okay, how it passed horizontal line test or not. So for y equals sine of x, goes up to 1, down to -1. I'm going to graph it pretty quickly because we've already done it before. Oops, almost started graphing cosine. That's 1 period. That's from 0 to 2 pi. And then that cycle repeats in all directions, left and right. Okay? This is not 1-to-1. Okay? If you remember horizontal line test, you can use that. If not, let me connect it back to the definition. Okay? I have some values here. Let's choose that one right there. This is pi over 2. I know that the sine of pi over 2 is 1. Okay, sine is the y value, pi over 2, it's still even up here. Okay, but go down the road. There's another y value of 1, right? There's another peak here. What is that value? Well, because sine is periodic with period 2 pi, if I add 2 pi, get a common denominator of 4 pi over 2, and I can be at the angle of 5 pi over 2, and I still have a sine value of 1. Okay, so I have an output 1 that is paired with, not exactly 1 input, but 2 inputs. That's a problem if we ever have to solve for inverse sine. Because if I want to take the inverse, I don't know if the inverse is this number, or that number, or possibly other numbers. Okay, so I start to have problems. How do I undo sine? Okay, so the answer to that, or our workaround solution, is to restrict the domain. So think about all these key words we're covering here. Function, inverse, 1-to-1, domain, all these terms that have popped up through the course are coming up again, tying in together nicely. Okay, so domain is all our inputs. So I'm going to restrict my inputs. Well, I'll restrict them to what? I'm going to restrict them to a region that will pass horizontal line test and will have a restricted value that is 1-to-1. Okay, so when I say restrict, and my choice is quite arbitrary here, but we always fundamentally make the same choice. I'm going to start my restriction at negative pi over 2. And I'm going to continue my restriction until pi over 2. So these values in here do pass horizontal line test, are 1-to-1, and if I'm talking about their inverses, I will have a function. Okay, so let me erase the parts that I'm no longer using. Right, if I'm talking about restricting the domain, I really only care about this blue section that I've highlighted. Okay, so when I said we restrict the domain, now I can say what we're restricting it to. Negative pi over 2 to positive pi over 2. Okay, what that means about the inverse, okay, is the following. If the original function had domain negative pi over 2 to pi over 2, that means sine inverse of x will have a range of these values. Right? When we remember doing inverses, the x's and y's swapped. That's like saying domain becomes range. So original function's domain becomes inverse's range. Okay. What does that mean about our visual? Right? Whenever possible, we're going to try to visualize what's going on. Okay. Well, pi over 2 is up here, so that is part of my answer. I could go from anywhere up to pi over 2, but I can't go beyond pi over 2. Okay. Or I could go backwards, which on the unit circle is to go clockwise. So if I go clockwise, a quarter circle, I'll be at negative pi over 2. Okay, so what this means for us visually is if I'm talking about sine inverse, all the outputs, all of the answers will be in this blue region on the right-hand side of unit circle. Okay, this is really all the development, and now we're going to do an example. So I need to create more space. All right, so here's our example. calculating the sine inverse of negative root 3 over 2. Okay, look at how different this is from the sine problems. Problems about sine would input an angle and output a number, right? We'd input maybe pi over 6, and we could output its sine value of a half. This is reversed. We're inputting in like a number from a triangle, and our output is going to be some angle. What angle? Right? Inputs and outputs are switching when we do inverses. So my answer should be some sort of an angle, and that angle is going to be between these two answers. Okay. So where does negative root 3 over 2 come from? Okay, we should have seen this number before. It comes from the 30, 60, 90 triangle. The fact that it's negative means it has to be below the x-axis. So it's a sine value, which means the y value has to be negative, which is why we're being below the x-axis. Okay, so if I think about how I might need to orient this to make it work, okay, right here, I've got these 30, 60, 90 parts, either remembered or I'm checking my triangle. Half, hypotenuse is always 1 because we're on unit circle, and root 3 over 2. So this is the triangle that's emerging, and I need to know what angle this is. Okay, notice it's clockwise formed, so it's going to be a negative angle, and it came from the 30, 60, 90 triangle. So is it the 30 degree or the 60 degree? It's not the 90 degree, that's over there, okay? Well, across from root 3 over 2 is always the 60 degree angle, always. But I can't answer in degrees because I'm supposed to be between pi over 2 and negative pi over 2. Degrees doesn't correspond to these measurements. So 60 degrees is the pi over 3 angle, but we are negative because we have gone clockwise. Okay, there's a lot of explanation that went into this, but it really just comes from this one guy. Okay, I had this as my y value. I made it my vertical distance. I formed my triangle. I remembered my triangle, and I remembered the angles from that triangle. That's all it takes. Okay, not done. We do another, and this one will involve cosine. So we already have our final answer for this problem. So cosine, let's go back to its graph. All right, so cosine of x started up at 1, made that shape from 0 to 2 pi, and then this cycle just repeats. Repeats, repeats, etc. Okay? We need to restrict its domain because it still doesn't pass horizontal line test. So we restrict its domain not on the same values, okay? But starting at 0 and continuing until we hit pi. Everything in this blue section will pass horizontal line test. So cosine is not 1-to-1, so we restrict it the domain to the interval from 0 to pi. Okay, what does that mean visually? It's not the same as the sine domain. Let me erase what we no longer need from the last problem and talk about where we're at. So if we're going from 0 to pi, that means instead of being on the right-hand side of the unit circle, we're going to be on the top half. Okay, just trying to go over that in black. Maybe it doesn't show up so well in the video, but the top half is now blue. So all our answers for cosine inverse are going to be between 0 and pi. So let's look at a problem here. Suppose we want to figure out the cosine inverse of negative root 2 over 2. Okay, that means again our answer is going to be some angle who has a cosine of negative root 2 over 2. Let me write that down, okay? What angle in this region, theta, in that region has a cosine equal to that value? That's what this is asking. Remember, inverses switch inputs and outputs? So taking a look at this, If the input becomes the output, that's exactly what's happening for cosine inverse. I need an angle answer that would have a cosine of negative root 2 over 2. Now, because I'm talking cosine, I'm talking the x value. So thinking about what angle has an x value when you draw the triangle of negative root 2 over 2, okay? It's negative. So it's going to be somewhere on the left of the origin, right? That's where the negative x values are. Negative root 2 over 2 comes from the 45, 45, 90 triangle. So I just have to make the x value be negative root 2 over 2. Here it is. Okay, negative root 2 over 2, because I know my 45, 45, 90 triangle. Positive root 2 over 2, hypotenuse is always 1. Again, vertical distance is always connecting to the x-axis. I always have a radius that's the hypotenuse of 1. So this boils down to, what is this angle? I know the reference angle is pi over 4. 45, 45, 90 triangle has radian measure pi over 4 and pi over 4. But that's not my theta answer. That's just the angle in the triangle. There's my theta, okay? I had this figure drawn up here on the previous video, okay? Remember how we had some symmetries here? If this is pi over 4, this is another pi over 4, there's another pi over 4, and I can just count them. 1 pi over 4, 2 pi over 4. Terminal side is at 3 pi over 4. That's my angle. I could also have done some fancy subtraction, maybe pi take away pi over 4, like 1 take away a quarter would give you 3/4. Well, 3/4 of pi is really what we have. So my answer is 3 pi over 4. Okay. So there's a tutorial on inverse trig. If you are asked a tan inverse problem, which I think WebAssign does, but I don't think I will do on the test, but I do want you to know how to do that, WebAssign. Tan inverse has outputs or range values or answers in the interval from negative pi over 2 to pi over 2, not including those endpoints, because remember the graph had vertical asymptotes, okay? So if you're looking for tan inverse answers, you're going to be in this zone, which is really the right-hand side of the unit circle, from pi over 2 to negative pi over 2, okay? All right, this should give you enough to complete WebAssigns, or at least continue to practice. As questions pop up, please don't hesitate to post into Schoology. That way I can answer if I'm available, but if I'm not available, good luck.